Hey guys, in this video, I'm going to show you an example, just an example of how a lens could be designed from scratch. But before we do that, um, I have to say that for many decades, and especially today, there's really no one actually does that. There's really no such thing as starting a lens from scratch. Everyone optimizes from a known state, such as from a patent or from a library of lens designs existing in a company's archives, and then going from there. And that's because obviously it's efficient, and a lot of the specifications you receive right now from many customers are so advanced and so challenging that you really wouldn't start from scratch. But in any case, um, here we'll try to start something from scratch. And so even though I'm starting from a blank screen, I'm actually not starting from a blank brain, right? Because from my experience, um, well, actually, sometimes I've started from a full brain and ended up with a completely blank brain because I may not know what I'm doing or whatever, right? It happens in many cases. But anyway, let's not go there. Um, Here, from experience, I already kind of know in my mind what I want to achieve here. A Cooke triplet, for example, three lenses. And so let's see how it goes, all right? Um, First, we want to check the system parameters. I have chosen my system aperture to float by stop size. That means I'm going to control the size of the aperture stop myself. And then I set ray aiming on because I know that in the Cooke triplet, I've got three lenses and a buried stop. What else? Okay, that's good. And let's see the field angle. I'll do that later. Wavelength is set to FD and C, which is kind of like a visible spectrum. So let me bring this plot here, which is blank for now. All right, let's say I've got a small stop because I don't want to over challenge myself here. This is impromptu, unscripted. I may not know what I'm doing here, right? I'm just gonna muck around and see. So let's say I've got, okay, Cooke triplet, right? Cooke triplet is three lenses, three elements, thin elements, and one positive, negative, positive, because you want to be able to correct the field curvature. You need positive surfaces, positive, negative combinations for that. Um, and the central lens is a flint-like glass, and then you've got crown-like glass for the front and back. So if I have three lenses, let's say there were three elements and they were all positive. And let's say I want my lens to have a 50 millimeter focal length, 50. Um, that means, let's say that all three lenses were 150 millimeters focal length. That means, because three of those together, using the thin lens equation together, will give you a 50 millimeter focal length lens. But of course, the middle lens has to be negative. So if I have 150, 150, and 150, I have a 50 millimeter lens, focal length lens. But if I have 150 minus 150 and then 150, then the first two are going to negate each other, right? Which is fine because I'm just starting from nowhere, right? Uh, I can also compensate that negation with the third lens, making the third lens 50 millimeter focal length. So let's just do that. Let's make the first lens, let's say BK7, because its index is about 1.5. It's easy to do some manual calculations and give it a thickness, say 8 millimeters or so. And then, okay, planar convex lens, let's say, right? Planar convex lens, what is the focal length equation for planar convex lens? 1 over f equals 1 over n minus 1 times 1 over r1 minus 1 over r2 plus thickness, blah, blah, blah. But if the thickness is 0 and if r2 is infinity, then 1 over f equals n minus 1 over r. If n is 1.5 roughly, you got 1 over f equals to 1 over 2r. And if r here is 75, f will be 150. So let's make it 75. And see the focal length at the bottom here is about 145, 150 or so, right? So that's fine. And then let me give some thicknesses here, and this is now a flint-like glass lens, 2.5, 2.5. Make it a thin 2 millimeter lens, and this is gonna be negative 75, let's say. Whoops, maybe negative 75 here, but infinity here. Okay, so let's take a look at what this looks like from the front. This is rather thick, so why don't we just halve these two? Okay, and then give this a third lens to be let's say NBK7. I don't know yet. Right now I don't know. I'm just fooling around. Um, 2.5, 2.5, and then give it a thickness, I don't know, 5 or so. And then this, I want this third lens to be 50 millimeters in focal length. So how about 25, right? It has to be 25. So that it's now, look, 54 at the bottom here. So it's close to 50. Good enough, right? Good enough for what we want to do. And then let's give this a marginal erase of. Okay, great. So that looks something like a triplet. Let's give a field angle. Choose anything. Okay, say 5 and then 10 or so. Okay, there we go. This lens looks kind of big for its field, so let's make it say 8, 8, 8, 8, 8. Looks better, right? Let's visualize the front further by adding a first dummy surface. Wow, that's kind of thick. Maybe make it 4, something like that. Okay, give it a bit more power. And it'll be like 52, 52, 65, 51, 60, 50, 49.99, 50. So now I got 50 millimeter lens. There we go, 50 millimeter lens. So this is not the design yet. This is just tweaking it. And then now we're going to put variables on it. Set variables. Yeah, put a variable on that, put a variable on that. You'll need these all the curvatures so that you can control the field curvature and other aberrations. In fact, all 6 aberrations, 6 parameters, 5 aberrations, and the last one is focal length can be controlled. And then give the thicknesses variables, except for this guy here because we don't need that to vary. Let's vary the last one as well. Okay, so good. Still kind of big for that. I mean, it's 7, 7, 7, 7. Does that look better? Well, it's kind of better, at least, especially the last lens. Okay, so good. Let's optimize it. So let's create the merit function. Um, let's drag this down here so you can see it. Okay. First of all, focal length. Center focal length should be 50. Put a weight of 1. And it's actually, I don't really need the weight of that high of a weight there. Okay, let's control the lens thicknesses. Minimum center thickness glass, minimum edge thickness glass, maximum center thickness glass. Control the total thickness from 2 to 7 inclusive, 2 to 7 inclusive. Operand, make it less than, make it, right now it's about 21, make it less than, say, 40. 40, yeah, I don't know, just give it something, right? Glasses from 2 to 8, 2 to 8, 2 to 8 in zone 1. This is obviously not for beginners. If you don't know what these are, maximum 2 to 8, maximum center thickness glass should be 10, I don't know, 10, minimum edge 1, let's say, center thickness minimum 2, let's say, okay, 2, okay. Let's control the air spaces with minimum center thickness air, minimum edge thickness air as well. The 3 to 7, 3 to 7, 3 to 7, 1, 1. Okay, center thickness air, I don't know, 1. Edge thickness 0.2. Just mucking around. Axial color, you don't really need that because it naturally finds it, but let's just put it in anyway. Put in a target of 0. That means I want the chromatic aberration between the blue and the red to be 0. It will not be 0 exactly, but that's okay. It's fine. Okay. Then let's add in operands for RMS spot size. RMS spot size just gets you near where you want it to be. It's not exactly, it doesn't always work very well if you want really high performance. But we'll add it there anyway. What will help us later on is RMS wavefront error. That relates more to the MTF, and we won't put weights there yet because we want to get just close. All right. So, okay. So what do we have right now for color, axial color, right? Chromatic aberration is probably not that well corrected yet. It's just varying there, and then the MTF may not be very bad actually. Not very bad. I mean, if you look at this, um, the actual MTF is usable. Actually, it's quite usable. Interesting, right? So maybe we're done. In fact, we're done depending on what you're trying to resolve here with this lens. If I wanted to resolve 4 cycles per millimeter, we're done, right? Put it at 4 or 5. um, it looks really good, right? Um, but if I want to resolve better than that, like, usually around 40 cycles per millimeter, it looks okay for the axial, but not that great for the off axis. So let's optimize this lens and see where we go. Let's just hammer it right away. Why not? Because why not? Right? And let's see where it goes. Because we're close. You use hammer when you're kind of close. So it's okay, not too bad. The off axis is better. On axis is not great. Okay, not great. That's fine. That's fine because what we'll do now is we're gonna switch to, because we're close now, we're gonna switch to RMS wavefront error, right? RMS wavefront error, and then oh, by the way, before we do that, let's check out focal shift. Not great because I didn't put a high weight there, but we'll just leave that weight around. Doesn't really matter. Our EFL is about 50. Okay, good enough. So let's optimize some more from here with the RMS wavefront error. Optimize. Let's hammer that. Push automatic. Oh, actually, you cannot see that optimization going on, right? The window, because again, this video capture software I'm using is somehow it doesn't really show some windows here. But when I'm optimizing, there's actually an optimization window out here, and you can't see it. What the heck? Anyway, it's optimized. Here is the MTF, much better, right? At 40 cycles per millimeter. This is a usable lens nominally. If you add tolerances, probably will come down. If you add some reasonable tolerances, each one will go down by maybe 10% or so, right? If it's reasonable. If it's like unreasonably loose, it'll be like 20% drop, probably, roughly. So and here's your triplet, and here's your, there we go. It's somewhat corrected, right? How's your field curvature? I didn't check that earlier on, but how's your, not really field, well, okay, sort of field curvature, but more like astigmatism. Okay, so if you look at this plot down up, try to expand that here. You've got a lot of astigmatism going on. It's not, I mean, you've got the curvature. A field, you only get an image field if your sagittal and tangential fields are together. Then you're not astigmatic. And then both of these surfaces rely on what's called the Petzval surface. And that's your field curvature. If you're split, you don't really have a field. There's no field, there's tangential and sagittal field. But if you can flatten either one, flatten the tangential field or the sagittal field, and put it at the image plane, you can cheat a little bit. I mean, if you've got enough photons and you don't need a lot of light, if you put a flat tangential field, which is doable, you can even do a flat tangential field or a flat sagittal field with a singlet. If you're monochromatic, right? You put that flat tangential field, for example, at the image plane. Now you got a flat tangential field, right? But if you take your aperture stop and make it into a vertical slit, then you only have tangential rays going through, right? Which is much reduced in light, in your light energy or photons, but it's flat, right? Pretty much flat. So that's one way to cheat. Anyway, this is good enough. I mean, this is really how to achieve field curvature, a flattened field without really correcting field curvature. You're not really flat, but you're good enough. You're good enough to have this MTF plot right here. So okay, so that's roughly how you can start from scratch and get some kind of rough design, right? And seems to work pretty okay. All right, and that's it. Bye bye.